So I'm Fabien Chouteau, software engineer from the company called ADA4. We are developing and maintaining tools for the software development, in particular with the ADA and Spark programming languages. Today I want to talk about the PAVES project that we worked on the last year. So PAVES stands for Open Platform for Autonomous Vehicles. So that's quite a big and ambitious name, let's say. And I will show you what's really behind this project. To begin with, I will show a short video demo of what the platform is capable of. So to give you a little bit of context, what you will see is this car over here that we developed. On top of it, there will be this module, which is an OpenMV camera. It's just a microcontroller with a small camera module. And the camera will run a line following algorithm, and it will drive the car. So just to show you, okay, working. So this is just a quick demo that I prepared before FOSDEM to show what the platform is capable of. So there was a few mistakes from me on this demo. First, the camera is really low, so it's difficult to have a good view of the track, and the lens is not a wide angle, so the view was really restricted. So here it's speed up a little bit. But still it's working quite reliably. As you can see, there's a lot of wobble, but I'm a software engineer, I'm not a control engineer, so my PID was not really well configured. Okay. PAVES. So the idea of this project comes from various autonomous vehicle competitions that we saw starting a few years ago. This one is from Audi, so you can see the cute little Audi cars that they provide this car to students, and they ask them to implement autonomous driving features on top of it. And at the end of the year, they have a small competition between the different teams. This is more or less the same principle. This one is called the Carolo. And there are also initiatives in the open source and some more hobbyist communities. This one is Formula Pi. It's quite interesting. You can actually log on the website. You submit a piece of code, and they will put it in the robots and have it run for you, so you can participate from a distance. This is very well robot car, I think. It's a group they meet up in San Francisco, I think, every month. And they just gather to play with autonomous cars and this kind of stuff. So they have a small track and they try to test the new algorithm over there. So really the PAVES project is inspired by those competitions. And what we wanted to do is to develop the platform. So the idea is to develop the vehicle that I showed you, develop a module on top of it, which is the advanced driver assistance system, which will control some of the features of the car, maybe collision avoidance, this kind of things. And then we do not implement the autopilot. We want to export an interface for hobbyists, students, etc., to actually use that platform to make their own autonomous algorithm. So why did we do this project? There's two main targets. First, as I said, as an open platform for students, researchers, hobbyists to use and play with this. And also for the ADA4 company, we use it as a demonstrator to show some of our technologies, and especially at trade shows where there's a lot of people going around, there's a lot of goods. So it's nice to have an object like this to demonstrate the practical example of what we can do with our tools. So let's look a little bit at the hardware. The requirements for the hardware are mainly those three, so capable of addressing the classical challenge of autonomous vehicles, so lane following, collision avoidance, and autonomous parking. We want the platform to be affordable, and we want it to be easy to buy or build. So if it's not available in the store, it should be easy to make it yourself. The main components of the design are those ones. So we have a microcontroller at the heart of the system. We have a Bluetooth module to be able to remote control the car when it's not in autonomous mode. We have an IMU, so gyroscope accelerometer. We have some range sensors that can detect objects or obstacles in front and behind the car. So it will give you a distance. Of course, we need some battery and some power control, motors, and a servo motor to control the steering, the direction. So one of the main ideas from the design is to use PCB as the frame of the car. I saw that idea online. Somebody tried it but didn't put the project to the end, so it was not really finished. So I inspired from this idea, I designed this small board. What's really nice here is that PCBs those days are really cheap to manufacture, and it's really nice to have all the wires from the same source, the microcontroller, everything in the PCB, so you don't have many wires on your vehicle. Next design choice is to use 3D printed parts. Also inspired by, I don't know if you heard about the OpenSC community and a guy called Daniel Norrie. He's doing a lot of nice vehicles with using 3D printing. And so some of the parts of the OBS car are made that way. So this is the first prototype. So as you can see, we have the PCB here, some 3D printed wheels. We even have the flexible material for the tires, the sensors here, etc. So when we looked at the first prototype regarding the different requirements for the hardware, so it was capable of addressing the challenges, it was affordable, under 200 euros, I think. Unfortunately, it was not really easy to buy or build. Not easy to buy because we are a software company, so we are not really used to manufacture and distribute this kind of hardware, so it was not really on the plan for us. And it was not easy to build because of all the small components like the microcontroller and the IMU, which you really need some advanced soldering skills to assemble the hardware. So we had to find a solution, and this is what we came up with. So don't be too excited, okay? We are not making a fake car. The idea here is just to take this off-the-shelf nano drone, which is called the Prettyfly. We take off the motors and we plug this drone on the car. What we get from this is that on the Prettyfly we already have the microcontroller, we already have the IMU, we already have the Bluetooth, so everything is done for us. What's left on the car is really easy to assemble. So this is the next version. It's not really the last version. Those wires are not here anymore, it's not clean. So as you can see, we have the drone here, the battery, 3D printed elements, etc. So all the hardware for PAVES was developed with open source software. So I think it's a nice example of what you can do with open source. So for the PCB, we used KCAD, and for the 3D model, we used FreeCAD. The hardware itself is available on GitHub, and we used it under the CERN open hardware license. So this is quite nice work. It's a rendering from KCAD. Okay, let's switch to the software side now. So this is an overview of the software architecture. So at the heart of the system, we have what we call the shared value and parameter database. The idea is that all the sensor values or the system values are stored in this module to be able to give access to the pilot module, everything from the system, including the pilot will write values in here that the advanced driver assistance system will use to control the car. So we have some sensor acquisition. We plan to have so SLAM is an algorithm to create a map of your environment. I put a question mark because it's not done yet, and the collision prediction as well. And so as I said, after the values from the sensor and the pilot are written to the database, the ADAS system will take those values and use that to control the car. So now if we have a look at the, this is more like zooming on this area here. So as I said, the idea for this project is not really to make the autonomous driving car, but more a platform that will allow you guys to make something out of it. And so that's what I try to explain here. So basically, we have an interface that we define. You can insert your autopilot. You will get the data from the sensors, the data status, etc. And you will send the autonomous pilot will send commands to control the car. And this is exactly what I did with the demo that we saw at the beginning. So in this case, the OpenMV camera that I have here is the autopilot, and it's sending commands to the OPEX platform. On the OpenMV camera, you have the computer vision algorithm that will detect the line, PI loop, etc. And so this one is running Python, but you could use a Raspberry Pi, for instance. You can put it on the board and use the same communication link to control the car with virtually any hardware that you So some of the tools and libraries that we use for this project. So as I said, I work for ADA Core, so we use the ADA and Spark programming languages. Also, we took some of the code for the small nano drone. We had an employee, Anthony, who rewrote the flight controller for this drone. So that's part of the code that we reused, which is partially in Spark. We use this project, which is an ADA project that provides a driver for microcontrollers like the STM32F4. We have support for the RISC-V Hi5 1 board as well. So that's for the drivers. So the Certify is the flight controller that I already mentioned. And we also use some of our tools. So NetProof is a tool that will run the formal proof analysis on the Spark language. And we use other tools like net coverage to compute the source coverage on some of the modules. Now the cost of the platform. So as I said, the reason to change the design was to make it more simple to build the platform. Unfortunately, the side effect is that the cost is quite bigger now. So PCBs, as I said, it's really cheap to have them manufactured nowadays. You can get 10 of them for $50 more or less, and that's if you get the most expensive version. The other components are all off-the-shelf parts on the Polo Robotics online store. So we have some motors, a few screws and nuts, battery, etc., etc. I think the most expensive in here are the range sensor because they are 13 euros a piece, something like that, and there's 5 of them. And then you have the price of the Crucify, which is 180, but of course you still have the ability to have the nano drone, which is pretty cool. So in the end, we are $380. The business is that is way less than this. Still pretty good. So now, what can you do with it? That's probably the most important part. So yeah, the idea is that this platform is open for everybody to experiment autonomous driving. We try to make it as easy as possible to build. If you have access to a 3D printer, you should be able to assemble the board easily. There are instructions on the interpreter to assemble the car. What are the potential improvements? So on the hardware side, we would really like to have encoders on the motors to be able to know the speed. Unfortunately, this is not really easy to do on such a small car. I didn't mention, but I think it's a 1/18th scale. Of course, you can change the PCB because I used the PreCFly on the drone, but if you want to change the PCB, make it compatible with your favorite microcontroller like the TZ, Arduino, Adafruit Phaser or something like that. On the software side, so there are two motors on the board, one for each wheel, so they are independent. And in theory, it would be nice to be able to control them independently to do the active differential, so giving more power to one wheel to improve the turning ability of the car. This is not done yet. And the sensors, so we have the drivers and we have the sensors on board, but we actually don't use them right now. So that's it for my presentation. We'll take the question right now, but what I really want to know is how are you going to change the platform and how are you going to build it? Thank you. Okay, so the question is why are we using a microcontroller instead of maybe something more powerful and potentially less expensive like Raspberry Pi or something? So we use that design because we know the PreCFly nanodrone, we know this microcontroller as something we support and we know very well. As I said, the platform is flexible. You have the design file, so it's completely possible to change it and use directly a Raspberry Pi or whatever. There's no real reason other than that's a platform that we know and we like it. So that's what we do. Yes? Sorry. That was the question is what is the ADAS layer does right now. Right now there's not a lot of stuff in it. It was supposed to implement the auto braking. So when there's an obstacle in front, brake the car before hitting it. As I said, we did not use the sensor yet, so that's not implemented so far. So yes, it's not that much. What we do have is a monitor that will stop the car if there's no remote connection. When you are driving it with, so I mentioned Bluetooth, but you can drive it with your smartphone using the same application as the nanodrone. So when you lose the connection, the ADAS will stop the car. Yes? Okay, so the question is why did we use the nanodrone instead of other boards with the same sensor? Okay, so I guess the answer is exactly the same as for your question. That's a platform that we know. We already developed the flight controller for it, so we already had all the drivers, all the software to run it, so it was really quick for us to reuse it. So yeah, originally on the drone part. So that was, as I mentioned, Anthony who did this. I think it proved the absence of runtime error on some of the stabilization algorithms, so the PAVES and these kind of things, and that we will use also for the base platform. And if you are interested by this aspect in particular, on the ADACOR blog, so blog.adacor.com, there is an article about the drone and the software that was developed with Spark for this drone. So if you are interested by this subject in particular, a good reference. Not really so far. I don't think ADACOR will do it, as I said, it's not really our business. Maybe if, for instance, the people that make the drone are interested, I don't know, we take most of the parts from the polygon, etc. Maybe that would be interesting. I will try to contact a few people like that. But really, you don't. It's really easy to have a PCB. I don't know if you already do something like this, but once you have a design file, it's really easy. And then everything else you can buy on the website. But yeah, it would be great to have a kit version. The price that I showed you on the website that I use, the service that I use, you always have to order 10 anyway. Yeah, you have at least $50. Maybe there are cheaper services, I'm not sure.